יום וחצי.
Astronauts to the moon.
Ignition sequence start. 3, 2, 1.
Houston, we have a problem.
Liftoff. We have a liftoff.
We copy you on the ground. You got a bunch of guys about to turn blue.
What you're seeing here is a mirage.
Are you ready? Debate fans, are you ready? For the handful in attendance and the thousands watching across the world, brought to you tonight by Jeranism,
for
the #1 YouTube
2,
channel
3, 4 miles. I have the camera guys there.
Ladies and gentlemen, let's get ready to rumble!
Make sure your argument is tight. Wait, what? You must got proof if you so right. Wait, what? Don't get dismissed on false claims, cause you gotta bring the truths and the facts. It don't matter if you're talking about racism, sexism, scientism, paganism, socialism, communism. Talk about capitalism, atheism, globalism. What about creationism? It don't matter what the ism. Live on debateism.
Welcome, everybody, to Debatism. We've got a fun show for you this evening. We've got Eyal Lev versus Shane St. Pierre. Let me get the thumbnail up there and we'll get you guys going. It is episode number 25. Okay, I knew that was going to happen. 1 second. There we go. Fixed it. Have some issues here when you haven't done the show in a while, but we will get it going here. So let me bring the guys on, say hello to them, and we shall get going. Sorry about the view here. It'll be fixed in a second. Let's start out with Eyal. You want to tell everybody who you are, where you're from, all that fun stuff? Please.
The name is Eyal. I'm from Israel. It's almost 6 a.m. here, so I'm kind of tired, but I stayed up for this. I've been debunking flat Earth stuff, I don't know, for almost 10 years, maybe even more. And we'll have a nice discussion here about optics and curvature, and we see how that goes.
Okay, excellent. And your opponent over here on the right is, of course, Shane St. Pierre from Ether Cosmology. Shane, what's up?
What's up, Jeremy? What's up, everyone? Good to be back. What's up to everyone over at Ether Cos hanging out watching? And what's up to all the Jeranism fans and everyone in the chat?
Nice. Okay, we're going to start out with, I believe, 1 minute introductions. And I think you're going to start, if I'm not mistaken, Shane. Is that correct?
Yep.
Okay. When you want, I will start your clock. And you can go ahead.
I'm ready. Let's roll. So we're going to have a nice discussion, I think, here with our opponent, Eyal, who's from Israel, I guess. We met on Twitter for accept my open debate challenge, as this is one of the topics. So this is going to be optics or Earth curve, focused probably largely around Rayleigh's criterion, angular resolution limit being compared to the geometric Earth curvature horizon and which distance you could find the horizon at, and how optics compares with physical Earth curve and the geometric curve that way. We'll also probably touch on other things that supposedly prove the curve or the geometric curvature of Earth, like bridges or reciprocal zenith angles, or the apparent the way for the horizon to rise to eye level. We'll probably touch on that, or any other topics I think that come up. I think we're pretty broad. We'll probably have some mathematical descriptions. I1 will be focusing on bottom-up obstruction and how that's perfectly possible on a flat plane and how that works with some math and basic descriptions. I think that's it. Over to you, Eyal.
Excellent. Thanks, Shane. Okay, go ahead whenever you want to start. Eyal, go ahead.
Okay, my points are basically, I'll just emphasize what Shane mentioned. Suspension bridges, how they are further apart at the top than they are at the bottom, which is explained by Earth's curvature. Reciprocal zenith angles is one of the ways we can check for curvature. It's supposed to sum up to 180 degrees if we have a flat plane, and in reality it seems to sum up to a higher amount than that. Radar horizon, like when they say flying under the radar, this is explained pretty well with curvature, because the ground is blocking the radio signal from the radar. Simple observations from high altitudes that show us more things than we can see from lower altitudes, also explained by curvature. And I would like to talk a little bit about science, philosophy in science, and how things are countered or not countered with different arguments. So that's about all, and we'll see how that goes.
Okay, thank you very much. We got a 30-minute clock for each of you, and it's going to be kind of back and forth, but let each other get a chance to talk. You'll each get 30 minutes. And let's get it started. I guess we'll start with Shane. You can start out, talk about anything you want, and we'll go from there.
Sure. So let's start with bridges, I think, because that's probably the easiest one to tackle. I think the claim brought forth was that suspension bridges in particular are built with Earth curvature in mind. We're going to dissuade everyone of that misunderstanding, of course. If you were to look at, say the one in particular, which you can definitely find noted on flatearth.ws, and Flat Earth debunkers beware, that is not where you want to be grabbing your Flat Earth debunking proof. However, they claim that the Verizon Narrows Bridge, right, claims that 1 5/8 inches further apart than the bases on top, meaning that that's a difference that engineers specifically accounted for because the Earth is curved. They're claiming that over that tiny distance of which that bridge spans, that the Earth curves a sufficient amount for them to have an offset on the top of their bridge dampers so that it's 1 5/8 inches further apart than at its base. However, when you have a suspension bridge in particular, it has to be designed for leaning and extra tension when it has heavy load. So that's not for Earth curve, right? All the suspension bridges are built that way. When they add weight, there's compression. They have to be able to flex. We do account into they have bridges experience expansion and contraction due to temperature changes, especially over seasonal changes. But so from winter to summer, they'd have to say compensate a swelling of a couple inches here and there. These changes become cumulative, of course, and together they can absolutely be more than the disparity that say they're building for Earth curve. Of course, you have the error tolerance regular in construction is going to be greater than the bridge's claimed requirement for divergence. And again, cumulative tolerative error tolerance cumulatively would at the end be more than whatever they're going to say they're accommodating for Earth curve. If you're going to compare other suspension bridges, the length of the bridge actually changes 12 inches between summer and winter. Again, a function of compression and optics and changing. And there, of course, when they're building it, they're accommodating it for that curvature, for that as well. Nothing for curvature. It's all about building stress, how they're going to handle loads, what kind of transportation is going to be, whether they have a dead load, meaning the static weight that they have regularly on the bridge, whether they're going to use the live load, meaning that the giant trucks that are moving and experiencing from suspension side to side, or the regular static load, right? But live load, particularly when it moves across a suspension type bridge, with that design has to be able to flatten out. So it has to be built like this so that when under stress and under weight, it actually flattens out. If it wasn't, it would break when those trucks go across. I think real quick, they also have some temperature changes. So like for thermal expansion, if you have a deck right there, you could expand considerably in hot weather. If you have A steel deck of 1,000-foot long bridge usually is 4.8 inches when the temperature rises from 20 degrees to like 120. So 4.8 inches of flex, if you will, between 1,000-foot long branch. And that's just an example. We mentioned seasonal variations, but let's just take a look at the Verrazano narrowed bridge, between summer and winter is 12 inches of expanded thermal expansion and contraction. That's way more than the claimed 1 5/8 inches that they're going to be handling to build for earth curve. Again, not accounting for suspension. Of course, you have the expansion joints, which are filling the gaps, which actually have to be designed to allow more stress. The bearings have to allow movement between the deck and the supporting piers. You have the basic flexible connections, which maintain on that static nature, which depend on the suspension and the tension created by the towers. I think that's pretty much it for bridges. What do you say to that, Eyal?
Interesting. Let me. Where's my? I'll share my screen for a second. Yeah, let's go. Okay. If someone is looking this later in the video, this is my opening statement. Just didn't have time to say all of it. So you can pause it and read it. But okay, we talked about, yes, you mentioned the same bridge. Basically, I forwarded this opening to you earlier. So yeah, you talked about the whatever bridge. One thing you said that sounds very odd. You said that the bridge gets longer because of material expansion. The bridges are anchored to the ground. Are the anchor points moving further apart when it gets colder or warmer? And I don't get how that takes place. Bridges are basically built in sections, and when the things get warmer, yeah, those sections expand, and there is a gap between them to allow room for those expansions to take place. But the anchor points, this is the towers on each side, do not get further up or closer apart because of thermal expansion. You're talking about they are leaning forward or leaning back to account for the weight of the bridge and when things get over it. But the measurement that was mentioned, the 1 5/8 inches, is measured from a perpendicular. When the towers are perpendicular to the ground, plumb. So a point from the top to the bottom, if you hang a weight, it's going straight down. So the tower is not leaning forward or back. And two towers on the two edges are both perpendicular to the ground, and yet the tops are further apart than the bottom, which means that they are not parallel, which means that the ground needs to be curved. Now, you can say, well, how do we know that this is the distance between them? And I will agree that I don't know exactly how this was measured, and any sort of measurement might be at fault. And I will also agree that this statement here in Wiki that says the curvature of the Earth was taken into account, I would disagree with this statement. You don't need to account for curvature when building stuff. You just need to be aware of it. But you don't need to account for it. They didn't put the towers so that the tops will be further apart. They just became further apart when they built them. You don't need to account for the curvature when you want to put a straight railway. You just need to go straight in level to the ground, and it will automatically be curving with the ground if the ground is curving. So yeah, if the ground is flat, then it will be flat. But if we're talking about a globe, then it will be automatically curving with the ground. So there's no need to account for curvature. It just happens this way. So I will agree that there is a good question to be asked on how did they know that this distance is as it is, but that's not the question right now. We are taking this statement as is because I didn't see you disagreeing with this statement. You're saying that yes, the tops are further apart in this distance. So you are agreeing with that. And if we're taking this as a given, then we have to accept that the towers is not parallel to each other, and the curvature of the Earth explains this.
Well, that's good. That was good. That was a nice rebuttal, except you just said the same thing, though. You just said that because they built it and because of the design, it absolutely accounts for curvature. I mean, the other explanations, the main one I think needs to be addressed, which is when they add weight, there's compression, so it has to be able to flex. So if a giant, series of tractor trailers are crossing this bridge and they built it to accommodate, just no stress, no tension, what would happen is when those joints are flexed, it would break essentially, right? If we're not going to say that, yeah. What do you think of that?
Not necessarily. If the flexing of the road does not mean that there is flexing in the towers themselves. The bridges are built in sections, and they flex with the distance between each section, not necessarily pulling or pushing the towers themselves. One can even say that if the towers are moving even a bit, it will cause fatigue in the material, which will cause the bridge to break. So one would say that the towers are specifically designed not to flex, but I'm not a bridge builder, neither are you. And again, we're taking this value that is given from the start, so even when there is no tension on the bridge. So it's a moot point of what happens when there is weight.
Well, in the first part, you said that I said that it moved. I didn't say the bridge moved, right? What I was talking about was thermal expansion, and the example I pulled was the steel deck of 1,000-foot-long bridge. That's not saying that it's moving. Obviously, it's anchored at the top, and we were first talking about the angle at the top, which was angled more than 90 degrees. But what I brought up was the example of 1,000-foot-long bridge expanding by 4.8 inches when the temperature rises. That's from 20 degrees to 120, it expands 4.8 inches. So if we're saying we're accommodating an inch and a little bit more for Earth curvature, but it breathes and ebbs and flows throughout the day to 4.8 inches, you see how that's not a good argument, right?
You cut out for a second there in the middle, but there is no connection at the top. I mean, if you allow me to draw him for a second, I'll just pull up paint and just to share. 1 second. We're saying that this is the ground. You want to make it a straight line. Let's make it a straight line for you. Yeah, like this. And this is one tower here and another tower here. And the bridge is basically going like this. Maybe it goes a little bit like this to allow for stress, or maybe it goes a little bit like this to allow for stress. Doesn't matter. But these two towers, A and B, are standing perpendicular to the ground at each point, and the distance measured between them, between the tops, there is nothing connecting them to each other. Yeah, sure, there is the lines, cables are going like this, but if you measure the distance between A and B, and if you measure the distance between, let's call it C and D, you get that A and B are further apart than C and D, and while both of them are perpendicular to the ground. And the only explanation for that is Earth curve, and the counter argument, the only counter argument that you can say is that one of these values is not correct, that they're not perpendicular to the ground, or that the distance between A and B is not different than the distance from C and D. So make your choice which one you want to question or invalidate. But if we're given that the distance A and B is bigger than C and D, and both of them are perpendicular to the ground, the only explanation is Earth curve.
Are you MS Paint certified? Did you get a degree for that? That's pretty good on the fly for doing it. But I see what you're saying. However, right, where I'm not saying that I'm making different explanations. I'm giving different varying gradations where they're accommodating for more than a 1.1 and a 5/8 inch variance throughout the different metrics of the bridge. First of all, with the heat, right? Then with the expansion, then with the flex. So what you're saying is that there is a difference in measurement from the bottom than at the top. but the steel at the top is not the same thickness than it would be at the bottom, nor would it be the same width. And then you have the deflection, which exists in all steel. So you're going to say above those variables and that amount, that's actually 0% of the account of 1 5/8 inches at the top, and it's actually all 100% earth curve at the top. Do you have measurements that would satisfy that 1 5/8 inch is actually measured for earth curve when you have, taken plumb measurements from each side to make sure it's level and to make sure that there's actually no discrepancy between them? Do you know how they derived at that?
Okay, yeah, and now we're back to what I mentioned earlier, and I completely agree that me right now, right here, I don't have, I've not measured those things myself. I have no knowledge of who did measure it, but I am assuming, maybe I'm wrong, but I'm assuming that whoever did this, one second, I'll share again, used a plumb from the top of A and measured it to the ground, marked wherever it is on the ground, and did the same thing with the second tower, and maybe using some sort of lasers or I don't know what. Well, I'm pretty sure that they didn't pull a string from one point to the other and measure the length of it, but measured it in a certain way, figure out the distance between A and B, use the same method to figure out the distance between C and D, and when C is the point where the plumb pointed to when it reached the ground. So it doesn't, so so it's not a matter of the towers being flexing or not, because you go from the top, take a plumb bob and see where it hits the ground, and you measure from there to the other side. So even if the tower is flexing or not, if they did it this way, it gives you the distance from the top and the distance from the bottom. And I don't know how they did it. I'm assuming they used some good way, accurate way to measure it. If we ever get the chance, I'd be happy to go with you and do these measurements with you together sometime, someday, but financially speaking, I have a few other things I need to worry about first.
No worries. I think that we can leave a bridges topic behind if you're good. I think that your explanation for 1 5/8, I think, is just earth curve is pretty weak. I think there's many other explanations for it, but I think we can agree to disagree. How about some bottom-up obstruction? What do you say? You want to go there?
I think that was my fourth point, right? High altitude observation.
You want to do how the horizon rises to eye level on a flat plane?
Yeah. Let's go over them one by one. So let's go with reciprocal zenith angles first, because that was my second point.
All right. You want to lay out a specific argument regarding reciprocal zenith angle?
Well, I'm sure you've heard it before, but yeah, sure. 1 second, I'll share the screen. Yeah, and this one. Okay. So basically, the idea is that you have a guy over here and a guy over here, and they're looking at each other, and they're measuring how much. It's a little bit difficult to explain it in this image, so I'll pull up my paint again. And we'll go with the flat ground first, because that is easier to understand. So let's see, this is the ground. And we have a person over here, and the nice thing about a reciprocal zenith angle is that you can have them at different altitude and it will work the same. So you have the two people here, and they are measuring the angle between zenith and the other person. Now, zenith is basically when you look straight up. So they measure this angle on one side, and they measure this angle on the other side. If we're on a flat plane, and it doesn't matter how far up one of the person is or how low the other person is, these two angles should sum up to 180 degrees. The reason for that is a little bit of geometry or math, but basically, if these two lines are parallel, then these two angles are the same. And this angle here is the opposite of 180 from that angle. So this angle plus this angle should be 180. However, if the ground is curved, we have something like this basically, and this angle plus this angle will not be equal to 180. So that is how we can know that, well, actually this example doesn't show it very well, but I'll try to draw it here. If here we have this thing, and we have person here, and we have the other person over here. The zenith for each one of them is like this basically, and the angle between them is this, or this is the line between them, and the angle here, obviously plus the angle here, is more than 180. So on a curved surface, or on a globe, the reciprocal zenith angles, the sum will be over 180, and this is how we can know that we are not on a flat surface. And I can later maybe show the links that I'm using here, but there are several measurements done by transcontinental triangulation of whatever, and you can see that the sum of the two angles are almost always, actually they are always more than 180 degrees. Now you could say that refraction has a part in this. The thing is that refraction actually makes it worse. Refraction will make this angle less than, will reduce the angle. So if we're still being over 180, despite refraction, this only proves that the curvature is there. That's basically it.
Okay. That's cool. That's a pretty good layout of the argument. Let's see if I can share database. Let's share the database. Not being shared. All right, cool. So the basis of reciprocal zenith angles, of course, as you outlaid it, is that they make measurements greater than 180 degrees. Do you happen to know the degree to which they are greater than 180 degrees on average?
Well, it depends on the distance, basically.
Certainly does. It's directly proportional to relationship to distance.
If it's 60 nautical miles, it's 1 degree, and if it's a fraction of 60 nautical miles, basically for each nautical mile, it's 1 minute of a degree.
When they're measuring reciprocal zenith angles, and they're measuring in arc seconds above 180, the typical Earth curve measurement verification is like 14 to 18 arc seconds. But there's a paper here that I like to reference. It's one of my favorites. It's called Monitoring of the Refraction Coefficient in the Lower Atmosphere Using a Controlled Setup of Simultaneous Reciprocal Vertical Angle Measurements. And it's from the Journal of Geophysical Research. There's a couple of different people named on it. But essentially, their experiment is to test the refraction gradient that you just so eloquently said actually only hurts the reciprocal zenith angles argument. But their angle was to test the refraction angle of terrestrial refraction at a typically above, grass surface, right about where you take reciprocal zenith angles measurements. And they apply the known method for simultaneous reciprocal vertical angle measurements to derive the coefficient of refraction, mostly known as K, right? So we know that as the 0.13, but they're going to test if the 0.13 is adequate for the measurements that they're taking, especially regarding trying to differentiate Earth curve between a variation of 14 to 15 arc seconds. So what they found when they did this is that when they not only allowed that determination of refraction independently, but they assessed the measurement errors from each pair. But what they found was that on cloudy days, the amplitudes of fluctuation were on the order of 0.5. That means it's going from K being 0.13 to K being 0.119. It varies between -4 and 16, which is a huge variation, well exceeding the determination of 16 arc seconds to make it to determine spherical excess. So this is on the ground near summer days. Of course, it varies between gradients between shortly after sunset and 1 day. They did these tests over many days, many different types. Their overall determination was that they were unable to say that 0.13 was sufficient for determining these. the actual measurements would far exceed a discrepancy. So when you go to comparing, say, 0.13 and 0.14, even that isn't really comparable, because even when you go to 0.17 and 0.15, you get a huge difference. If you look at 7/6R, the typical downward bending refraction gradient, that's something like 0.19, I think. So that's like a 22% difference just based off the 0.16 and 0.17. So when we're taking measurements of arc seconds in tiny measurements like that, then we really need to be careful that we're not measuring in degrees bigger than the error margin for reciprocal zenith angles. You did mention another American arc of the parallel, which is a brief triangulation. I just want to get into that real quick, because they do use the same method of theodolites and total stations and taking reciprocal zenith angles based off optical measurements. But what they don't tell you is all of the corrections that they have to make to the geographic long lat system, which happens to be the most important part of their measurements when they get over to it. Let's see here. Let's switch this over. Switch. How do I stop share? Stop share or stop share. Switch share. Images. There we go. So they needed to do geodesic surveying, or to do the Earth's dimensions must be known, because they make computations back to this coordinate system when they make corrections. We talk about this rather frequently. If we go over to this, there we go. This is from the American arc of the parallel. This is from the table of contents. What they make is ridiculous amounts of corrections to long lat tables, to astrogeodetic tables, to astronomical measurements, and they have star catalogs where they make latitude longitude measurements, which of course are pure on a spherical graticule based off of angles from the stars. They have these measurements for various longitudes. They're doing corrections directly to the long lat system for the American arc of the parallel. So all of those optical measurements above 180 are directly resultant of these corrections when they put in, because the first thing that you should know is that when they start the American arc of the parallel, the corrections have been introduced for the first time, and the entries that they're putting there are actually already been corrected. All right, so they said, although the number of stack catalogs have been greatly multiplied, they are making more corrections. So let me find out where it actually specifies which spheroid model they're correcting to. In this case, they changed the model midway. This is page 837. They had adjusted their spheroid reference spheroid from which they're going to apply the direct planar measurements to. Of course, when they throw it out, they don't, if it doesn't comport with 8 inches per mile squared, these measurements get thrown out. And when these geodetic differences are mentioned, if right here, rejecting all issues greater than 8 inches per mile squared. So if they choose their Clark spheroid model and it doesn't comport, they choose a different model until it does comport. They throw out all other measurements. That's how they get so nice and clean. This is on page 18. It says, for the first time, corrections have been introduced, right? So they're trying to correct the long lat all the time. So that's the American arc of the parallel with the various corrections to geographic long lat, and then the basic refutation to reciprocal zenith angles with the coefficient of refraction not being sufficient for accommodating spherical excess of 17 arc seconds.
Where did they mention something about 8 inches per mile squared? Can you show that for a second? Because that would be surprising to see that they're talking about that.
You mean in the American arc of the parallel?
Yeah, 8 inches per mile squared. I'm not saying that they don't, but I would like to see it if you can.
Yeah, let me share it again.
I don't. What did he say? Squared. I see 8 inches, but
it's hard to read for us to read. It says after rejecting all values, thank you, greater than what?
Yeah, greater than 8.
Yeah.
Yeah, but I don't see anything about squared or anything like that. Do they explain why 8 inches?
It's based on the model up here. So they had this metric based on comparing it to the model, and they were making these corrections. So it's given in the context of correcting back to the geographic long lat. So they can't correct with these inches, with these measurements greater than 8 inches. They didn't want to use them. So
okay,
they used tabular values.
Okay. This is something to maybe explore later, but it would be interesting to see where they come up with these 8 inches, because they're not saying anything here about miles squared or anything like that. Just there is an 8 inches. Maybe they explain somewhere else, but it would be interesting to see where did that 8 inches come from.
Sure.
It doesn't necessarily mean 8 inches per mile squared. So that was my question. But okay, regardless. So basically, your refutation is saying that we don't know how they did it. We think they did it inaccurately. If it was me, I would have done it better. That's basically what you're saying.
No, I'm saying that they did it by making planar measurements and repeatedly correcting to an ellipsoid spherical model from which they got the spherical excess measurements that you showed.
Yeah, which you're saying is the wrong way to do it.
Well, if you're going to measure the Earth, you'd want to look at the Earth. You wouldn't want to look at the stars and then correct your Earth measurement to the stars, would you?
Again, so basically what you're saying is that if it was you measuring reciprocal zenith angles, you would have done it differently than the way that the American arc of the parallel did. Basically, again, that you would measure it differently.
Well, I wanted to make sure that the reciprocal zenith angles argument was noted because this basic coefficient of refraction, as I noted from that paper, varies widely and has a huge effect. And they determined that the actual effects of refraction far exceed the so-called measurements of Earth curve exceeding 180. So that was the main point. And then above that, it could specifically on the American arc of the parallel, they made repeated planar measurements with spherical excess hiding in the corrections to the spherical model. And the bigger the distance, the bigger the correction, right? So a specific linear relationship for sure.
Okay, it's something to look into maybe some other point later. But basically the question is, what was the actual measurement that they did before the correction? And okay, me and you, we don't know it just now. Maybe we'll have to look into it deeper or get an expert that can tell us what exactly was the actual measurement without the correction. So,
all right, you want to move on?
Yeah. Next point. Next point was radar horizon. Let me just share my screen here. There you go. Sure. It should do it, yeah. And where is it? Here. So basically, here is an example. We can see the screen right here. Basically, here is an example of what is known as flying under the radar. The radar station, obviously exaggerated, but the radar station is over here, the plane is over here, and because of the Earth blocking the view for the radar, the plane is not visible. This means that the plane needs to fly very low and even lower the closer it gets to the radar station, but basically this is how in movies they say that they fly under the radar, but this is something that happens in real life as well. Planes fly very low to not get detected, and that's how it works basically. And to you, how do you explain it?
For sure. This is one of our favorites, actually. So let me share database again. Something called the Battle of the Beams is our best example for radar horizon, World War II. There was a Rolls-Royce factory that the Germans tried to bomb. They did so by setting up a Nick and Bond line of sight radar beam system, which had to maintain an equisignal from the point of dispersion, which would align over the target, meaning that this line has to hit this target. It has an equisignal over here guiding the plane, meaning if it got too left, it'd be a beep. If it went too far right, it'd be a longer beep. They had to stay in the middle. They had another beam hitting the same target from another spot over here. And when the beams intersected, they got a single unified tone that would give them the signal to drop the bombs. The problem with this setup is that it's far exceeding the radiogeometric horizon that you just laid out. The first point was actually, let's see here, was in Stolberg to Derby, and that's 451 miles. The next one was Cleve to Derby, and those are the two radar horizon points we were intersecting over here. And if you do the math for the Earth curve calculator, you'd see that they're actually way out of line. You have to be behind such huge amount of curvature, right? We did all the math to work it out. The actual radio horizon would make this particular feat impossible. The beam would hit the Earth curve at 31 miles. Derby's actually 50 miles shy of Spalding. It is an ultra high frequency. So all of this is the data, but the main problem is that it'd be blocked by a significant height, about 100,000 feet to the Earth's curvature. This factory should still be there today if Earth was a ball. It's been blown to shit. It isn't. They attacked it for every day for a year. They attacked it so hard that they had to resign, and they eventually intercepted the signal and confused them all and stopped the bombing. But this was a very successful radar attempt horizon, defying the actual radar horizon that you just laid out. And it's the most well-known example that we can think of. What do you think of that?
I see you have a screen there with radar with radio signal bouncing off the ionosphere. Does that have anything to do with it?
Well, this is the absolute illustration of how it couldn't work, because one of the proponents put forth a paper saying that this is how they could actually bounce off the ionosphere and have a skip zone, and that could actually work. The problem with that is this particular signal is line of sight, and if it's blocked by physical Earth curve for one fraction, it cannot recombine itself into its full consistency to once more display the equisignal beam. So if it was blocked or refracted, the purpose of the beam would no longer work. It would no longer be able to maintain the tones for the signal, for the dispersion to maintain this equisignal. So any sort of ionospheric of scattering or bouncing back immediately would make it not work.
Explain again why it wouldn't work. I don't understand.
So it's a line of sight.
If you get the signal, you get the signal.
Well, so it has to maintain the signal. So the plane flies in the signal all the way to the target, and it keeps in this equisignal. So this is two overlapping signals put forth by the big radar tower that looks a lot like this. Yeah, the naked beam tower. So they have them lined up to send line of sight signals. Here, let's find it. Here's the factory that they destroyed. Here's what they would look like. They're literally line of sight towers. So they go completely one direction, right? And that's how you get the measurement for how we got there. This is, they can align and they can kind of concave and convex to overlap, so they can get the equisignal from each one, but each one of these sides is a tower. Now, the second that this signal would skip, it would become impossible to recombine, because it has to maintain this signal completely between the line of sight and when they were to drop it. So this, again, signal was from 400 miles away from Germany over this Rolls-Royce factory, and they bombed this every day for a year.
Okay. Allow me to explain how I think it's going on. And 1 second. Share here. Okay. Let's see. So we have this thing here. Or maybe let's do it like this. Okay, so we have the radar station over here, and we have the target that we want to get to, that is over here somewhere. Now, what you're saying basically is that the target is blocked by the Earth, and what I'm saying is that let's put this one. This is the ionosphere, and what you're saying is that if they bounce the signal like this, then it will be cut off in the middle of the way.
Yeah, then they wouldn't combine over the target. They wouldn't get the equisignal. They wouldn't hear the tone when they were over the target. They wouldn't be able to drop it. None of it would work.
Yeah. Now, here's the thing. What if they're not sending a single line, sending a wall? So this one is going to be bounced like this, and this one is going to be bounced like this. Basically, the tower is sending a signal in a single direction over ground, but it's sending it up and down in the same direction. But it's sending it like not just a few beams, but basically a whole. Let's see if we can have it. It's a little bit too wide. Basically, like this. And so once the plane gets too far away to get the signal directly, it is already far enough to get the signal indirectly. So there is no skipping. It's either there is an overlap with the bounce. The bouncing is not just after a few miles, then it gets the bounce. It gets the bounce almost all the time with the signal that's coming directly. At some point, it doesn't get the direct signal anymore, but then it does get more of the bounced signals. So there is no cut in the in the signal detection. Once, if it veers too much to the right or to the left, then it will no longer get the bounced signal. So it will know to correct to go back to the right or back to the left accordingly. But because there is a wall of signals coming out and being bounced back, that could be how that is detected. And I would like, at a later point, I would like to look at the math and do this, the calculation you did as well. But if we're talking about the ionosphere bouncing, it's not just a single line that gets bounced. They're bouncing several lines. And, well, more than a several, it's almost a wall. So that's how I think they did it.
Well, I mean, that's an admirable effort, but have you ever looked into the Nickenbein system? Have you heard about Battle of the Beams before, or is this the first time you heard about it?
I might have heard it once a long time ago, but I would look into it. But I would have to guess that this is what happens. But yeah.
Right. So, I mean, we already did the diagram. You did a nice on-the-fly diagram of how you think it would work, but that specific setup with a bouncing or a scatter would absolutely break the system. It would absolutely not work. So we built this little diagram. Wait, am I showing? Yeah, I am.
Yeah, you're showing.
There we go. So it would say, here's the height, here's what it would have to be, here's the actual battle that you'd have to compensate, right? So the geometry of it is what you're fighting, 19,000 feet, and it's got a 450 to 500 wide equisignal. We know that for a fact. That's how the English actually stopped it. They picked up and intercepted the signal, so they knew how far and how wide it was over at England. So they did the math backwards and they figured out where it would have come from. So that's the math problem essentially, right? So what you just outlined would absolutely not work. It would take these planes completely out of the signal. They wouldn't have dropped the bombs. They wouldn't have been able to know where they were. They wouldn't have been able to know where they were coming. However, it was an admirable effort.
I didn't understand how it would take the planes out of the signal.
So the way that the system works is they need to maintain in the signal completely. If they leave the signal, then they can't hear the dome. They don't know where they are. They're essentially flying blind and dark in this. So they need the signal from the point where they enter enemy territory, essentially, until when they drop the bomb. And when they drop the bomb, they intersect the second signal, which gives them the final tone to let them know to drop the payload. And based on the map and where they are and the geographic long lat, then they're going to know exactly where they are. So they need to be in the signal the whole time. If it was to be bouncing and it was to enter a skip zone when they were over the city and they stopped getting the signal, they would freeze and not know what to do. Here's the other math of the diffracted beam, because it would have to be 18,340 feet, and it's 3.47 miles down to the beam size. So we mapped out what it would have to be on the globe. We gave every consideration for the height of the tower, sea level, all the differences and disparity, and there's no mathematically that it would work for a geometric globe.
The thing that you didn't understand from my explanation is that there is no skip zone. There is no time that it no longer gets the signal and then has to fly blind. It receives the signal, the line of sight, and also receives the signal that is being bounced. And at some point when it gets too far away to receive the direct signal, it keeps on receiving the bounced signal. And the bounced signal is not just a single line that is bounced down. It's like a wall of signals that all of them are bouncing at different locations. So the plane is always getting the signal, either the direct signal or the bounced signal. So the only limitation is this. Let me share again. Yeah, no problem. The only limitation would be, see if I can undo all of this. The only limitation, it's overscale it like this. And the ionosphere, let's say, is over here. So the limitation is that if the tower, let's say, is over here, sending out the signal, something like this. and this is the bound signal. And basically that is the limitation. If the target is over here, it won't be able to get it, because this is as far as it can get the bound signal, because this bound signal is blocked by the ground over here. The original signal is blocked by the ground over here, bouncing over here, reaches the ground here. So if the target is over here, we will not be able to hit it. But if it's over here, yeah, we will be able to hit it. So this is the limitation for my method, and all the other see, the signal that gets bounced here is also here. Now there is no skip zone. It's like there is a wall of signals that's going in all of these, so it doesn't lose connection at any time. It's at some point in time it loses the connection from the direct line, but it is always hearing the bounced signal from all of these ones. So the limitation is, once the bounce signal is hitting the ground, the farthest most bounce signal, then it cannot get this the signal anymore further than that. So
right, no,
would be interesting to do the math for this and see if this works.
Well, I mean, they put the math for that forward during the time that they were getting bombed, and they actually rejected it. And the big radio expert, I think Ecker Keskely, had withdrawn that specific paper as the method that it wouldn't work during the war. So the experts at the time considered that, and they, when they're basing their whole livelihood and safety of the country on it, they actually came away with a different sentiment, and they had canned it immediately and withdrawn it. But if we look at, let's see here, where's my thing going? I'm sharing this. Didn't work last time. So this, can you see the math that we're working out for the actual echo signal and the beam and everything?
Yeah, I don't understand why you're having the plane flying up. I mean, it's gonna be the same altitude from the ground.
So it has to maintain contact with this signal, or the system won't work, right? So they were guided with a laser system, a line of sight system, essentially, all the way through the target. So the scattering of ionospheric scattering would not work whatsoever. The person who put forward that idea during the war, let's see if I can find it. No, there it is.
Yeah, but obviously this is not how it works. Yeah.
Well, this is what you just proposed, right? Essentially, this exact scattering, the maximum delay signal would be.
Oh yeah, this one. Yeah, this one.
Yep.
Yeah.
So this is what he put forth, and this is absolutely how not the system works. This would not work. It needs to maintain equisignal. So the second that it bounces once, it's broken. This would not work, and they withdrew this from the time of the war. So the person who put this forward actually. It's from Eckersonly, TL. It's called Multiple Signals in Shortwave Transmissions. It was put forth from the Proceedings of the Institute of Radio Engineers in number 1, edition 106. So
I don't understand why you're saying that it wouldn't work. I mean, it's not like they're losing the signals. Let's keep this on, okay? So we have 5, 4, 3, 2. These are the lines. Now, it's not going to send only those 4 lines. It's not sending only 2, 3, 4, and 5. It's sending all of the signals in between as well. There are multiple other lines between the 2 and the 3, and between the 3 and the 4, and the plane is hearing all of those in between lines. It's the same signal in all of them. So the plane, it doesn't need to change frequency. It's listening to the same frequency, and it doesn't matter. The plane doesn't care if he's getting line number 5 or line number 4 or all of that. He's getting the same signal over the radio on the same frequency, and that's how it knows if it's on track or not. It doesn't care if it's a bounced signal or a direct signal. It doesn't even know if it is that or the other.
Well, no, they know. They specifically measured it at the equisignal range. So they measured it at 450 to 500 yards, 270 miles out. So that can't happen if it's bouncing, right? It was made to adjust to the equisignal. The whole bounce argument is null and void. However, did you want to go on to bottom-up obstruction?
Okay, let's go to the next one. Yeah, and let's see what I have here. Okay, high altitude observation, and I have this. Let's see, where did it go? Over here. Yeah. Okay, and I can share. Yeah. Okay. this guy over here is talking about kayaking, and basically he's giving out this picture here, and he also explains what's going on. But basically, this picture was taken at about 2 meters above the ground. Then he went a little bit further back up a hill, and now he took another picture. These two are like a few seconds, minutes apart, and with the same camera at the same zoom setting, and the 12 meters picture is even taken further back on a hill that was further back on the beach that he was standing on, and the 2 meter picture we can see that half of the boat is missing, and once he's a bit higher, then he can see the bottom of the boat. Basically showing that the reason that we don't see the bottom of the boat is not because it's too far away for us to resolve the image, but because it's being hidden behind the curvature of the Earth.
Okay.
Now do you want me to keep this up, or you want to share?
I got something else to share. So that's definitely the typical Glover position, is that the bottom-up obstruction of objects is specifically due to physical Earth curve. However,
not only, but mainly.
No?
I mean, there are other things that are in the way, but in this example, we can specifically see that there is nothing else going on the horizon. But yeah, in other cases, if there is a lot of smog or other stuff, then yeah, that could also factor into it. But in this case that I'm showing, there is no smog or stuff like that.
Sure. But if we're arguing that it's actually an effect of optics, meaning that if you're looking at the horizon, if your eye level is specifically in the middle. Oh, wait, am I sharing? Let's see.
Yeah.
Sorry, I'll share.
Okay. Yep. So if your eye line is specifically in the middle, then you'd have the top and the bottom of the object recede or disappear equally. Or in other words, equal angles disappear equally, but unequal angles cannot. So when you're in the middle, exactly in the middle, like over this on the illustration, if you're in the middle of the bottle over here, then you're going to have equal disappearance. If your eye line is closer to the bottom, you're going to have a much shallower angle to the object for the horizon for the bottom half than the top, and the unequal angles then will decrease unequally, meaning the bottom will decrease at a steeper rate than the top, and you would have what is called optics at bottom of obstruction. This diagram right here shows exactly the same thing, is that unequal angles cannot disappear equally, and if your eye is not specifically in the middle between the top and the bottom limit, then of course it will disappear it'll disappear quicker to the edge which your eye line is closer to. In this case, it's almost always the bottom. If your eye line is observing the horizon, then the bottom angles will increase equally. If you want to look at this GeoGebra model, essentially is showing you the same thing. It has to increase equally. Well, I messed this up before, right? So if they're in the middle, then only in the exact middle will the top and the bottom decrease proportionately. When you're looking at the horizon from eye level, it's more like this angle, where this is way disproportionate to the top. The top's much greater angle. This is much more steeper down here. If this was an effect of optics, you should be able to reverse it, meaning we should be able to replicate top-down obstruction under different circumstances. And that's exactly what you can do when looking under a tall building. If you have the same disposition from looking under a tall building and approaching it, if there's an observer over here waving a blanket out a window, as you can see them here, if you approach the building, the closer you get, the more information will be lost up top. What we have is the same in reverse compression of these top angles, which will increase disproportionately to the bottom. So if that's true, then you should get the same information we should be able to replicate it from walking into a building. And I think I did this the other day. When I walked right into a building, you lost the information up top here, and you can see that we have the actual compression differing from the top and the bottom. So we've replicated top-down obstruction based on optics, looking up just at a building. What do you think?
Not to be too insulting, but basically that was a word salad. But let me explain why. I know that it's not nice to use that word, but I'll explain why. What you're saying basically is that because we are low, we are unable to see the bottom part, and because we're getting higher, then we can see the bottom part. But if your argument is correct, that means that as we get higher, the top should disappear.
But that's what I illustrated with the building, right? You lose information at the top.
how far up would I have to be in my example? Let me show you my example again. Okay, in this example here, how far up will the person have to be in order for the boat to start disappearing top down?
You have to be on the ceiling. Like when you're at the horizon, the bottom limit is so much greater than the top. This top skybox is so much higher up. The boat would have to be on top of the sky, right? That's why you never see that. That's why the appropriate angle conversion is looking up at a building, because that's where you get the vertical compression angles in an analogous situation.
Let me do it here. Let me see this. Let's say we have this flat plane again, and we have our guy over here. Make him very small this time. This one. Okay, we have this. Let's say this is our guy. This is his eyes, very big eyes, and this is our boat here. A little bit under the water, but mostly here, and make it a sailboat, like a number 4. Okay, so because the guy here is very low, you're saying that's the reason this part of the boat is disappeared, because it's below the eye level of the guy. Now, if my person was up here, let's say this is his eyes, then for the same reason that we don't see the bottom of the boat for this guy, then this guy should not be able to see the top of the boat for the exact same reason. But that never happens. It doesn't matter how up you go, the top of the boat never disappears.
He'll just be able to see more of the bottom than the person on the bottom, right?
Yes, but the top never disappears.
Well, so that means we're not changing the angles, right? You're not changing the position so that the top skybox is the same proportion closer as it is on the bottom horizon. That's nowhere near the close. You just put a guy at 100-foot observer height above where the guy was. Of course, he's going to see more of the bottom that was been obstructed. He has a higher observation angle. One of the main things that affects where the angular resolution takes place is height of observation and the size, right? So you get distance and height. But the building example, when you're approaching a building from underneath it, you have the same vertical compression taking place in reverse. And in that case, the loss of information does occur in reverse. It occurs top down. You lose the topmost floors as they compress quickly. The points of resolution between the top floor and the one below that, you want to say those as angular resolution and Rayleigh's disks, then when they compress to become one, the information that was differentiable between them becomes unresolvable. Therefore, the loss of information would be, instead of at the horizon, would be vertical at the top. And that's what the building shows specifically, meaning that the loss of information at the bottom horizon must also be an optical effect.
Okay. Let me explain it like this. We have these two observers, one up here, one down here, and there are two features on the boat. One yellow window, that's pretty low, and a green crow's nest at the top of the mast. Now, you agree that this guy here, the low guy, he will be able to see the green nest, but he will not be able to see the yellow window because of your explanation that shallow angles and all of that.
Now, the resolution limit of optics, sure.
Yeah. Now, consider the top guy. Now, the same thing that was true for the low guy is true for the top guy about the crow's nest. Because if the low guy cannot see the low part of the boat because of low angle of resolution, then the same is true for the top guy that is at the same height as the boat. Let's say the boat is like, 50 meters high? That's a very tall boat. But the same amount of height that the boat is, this guy is, he could be like at the top of a building or something like that. Buildings are as tall as boats, right? So he's looking at the boat from the top of a building. Then since the low guy could not see the yellow window, the top guy would not be able to see the green crow nest. But we know that this doesn't happen. In fact, the higher you are, the more of the boat you see. The boats never disappear top down.
No, I agree. Boats never disappear top down.
So if the low angle of resolution for this thing is causing this one to disappear, the same thing should happen for the green crow nest for the guy on top, because it's the same angles.
Well, let's do one more share on my side. I think we're almost out of time. Can't read that. Yeah, I got 5 minutes. So let's do one more share on this side. I got one more slide. Let's do Canva. No, let's do present mode. And there we go. Canva. So there we go. If we see over here, we have the same example. We're going to lay out an optics bottom-up obstruction in a warehouse. This is with a laser light. We can do the similar example with our Flat Earth Netherland brother did it with a laser and some netting. So what he did is he set up a bottom limit and a top limit representing in this netting over here. He's got a bottom horizon and a top horizon. They are very linear and straight. He's got a laser in the back. He's going to move it forward and back. We're going to mimic the sun rising and setting. We're going to also mimic the bottom of the sun disappearing first due to the exact limit that I just went over, meaning that this observer is lower to the bottom horizon. So when this starts to meld and go below this, he's going to start to see it merge into this horizon and then disappear. So right here, you see the bottom obstruction, you see the lower angles compressing on the half of that little light, and we see it disappearing bottom up. And also, we're going to see it fade away into nothing. So we're going to see mimic the sunset, bottom up obstruction on a flat plane. What do you think?
Yeah, first of all, we don't see it disappear into nothing. We see that the net is blocking it. Now, several issues about this. First, fields and warehouses are not flat. They are curved to allow for drainage. This is also true for free wall field, and so that's one thing. Another thing, we have no way of knowing if these nets are in fact parallel, and we have no way of knowing if they are level. They could be angled, even if by mistake. Here's another problem. They cannot be parallel and level because they have weight. And if you take a string and even you try to with your own hands, it will always have a little bit of a curve to it. Try to pull it even stronger, it will still have a bit of a curve to it, especially if it is a very long string, like what he has there, like 5 meters or something. It will always have like a curve in it. The only way to avoid seeing this curve is if you have one end a little bit higher, and then there will be a little bit of curve, but it will be, it won't bend down below the starting point of it. So that is a possibility of what happened there. So without being able to test it, we cannot really say if he did it correctly.
It's time right there.
Well, all right.
You got time left, Shane.
Nice.
Okay.
Yeah, let's wrap it up with Skunk Bay because we have this famous time lapse of this, 1 hour. This is 1 day of the time lapse, and we see the horizon. Not only is the horizon line changing and ebbing, but all the buildings in representative size are shrinking and contracting and expanding. And if we were to look at this over a certain time frame, we'd get something like this, where we have all this compression and high compression over various days. Over a time lapse, we see various heights of objects, various thicknesses, compressions. What that means is if you were to overlay them, they were all at different heights. So if we're going to make arguments based on the bottom of objects being obstructed due to Earth curve, but then we have just one in 1 day, we must have a wobbly Earth curve for this to make so many different changes. Or we could have a horizon, which is a function of optics, which is literally defined as where the sky appears to meet the ground, and therefore as a function of optics would be variable based on the various attributes: wavelength, diameter, aperture, focal length, observer height, atmospheric opacity, light attenuation. All of these things will have an effect optically, especially in concentrated at the surface. So that's why when we say when we're looking at observations like this, the bottom of object should take a back seat to the tops, right? The bottom of object should take a back seat to observing the tops, because there's too much distortion near sea level to make sweeping claims unless refraction is at a minimum, and here it's at a maximum. As an example, if you look through the lines here, this is exactly what we're saying. So when we're looking at bottom obstruction is a function of optics. We have proved it, I think, because once we can mimic it going on a horizontal line, then you should be able to mimic it vertically. And you can absolutely mimic it vertically because what's happening in one area is definitely happening in another, right? If we have this horizontally and losing information as this compresses...
Okay, yeah, now we can see it, yeah. Took a few minutes to load, yeah.
And then when we go up, we can see that we're losing information at the top. So again, anything to do with replication, right? This is horizontal. This is what we're happening. This is what I'm saying happens to the boat. This is what I'm saying happens to the sun. And when we take it into practice, we should be able to reverse it and replicate it. And look, lo and behold, The top floors have become compressed way faster than the bottom. I've lost visual information to be displayed up here. Honestly, that's pretty much it. I think I'm pretty much burnt out.
Okay. There is something.
Do you guys want to do any outros or?
Yeah. Let me just reply a few things.
What do you want? 2 minutes to do an outro or what?
Yeah, something like that.
Okay.
2 minutes, whatever.
Go ahead.
Okay. The thing about one way, a very interesting way to check things out is, like you said, to look vertically, and that can be a few interesting experiments to do. Using buildings for it is not a very good idea. Most buildings are not perfectly perpendicular. They are tapered inward, so they don't fall. So that's not exactly a good way to do it. But if we could construct something when we have a beam that is very high, we can maybe do some sort of test about that. But that's beside the point. What I would like to, with the few minutes I have left to talk about is the philosophy of science. And basically, in all of this debate we had here, you did not disprove curvature. You provided, or at least you tried to provide an alternative explanation to what we see in curvature. The thing with science is that having an alternative explanation is not enough. If you want to debunk curvature, if you want to say that the reason that there is bottom-up obstruction is not because of Earth curve, you need to debunk Earth curve. Providing another explanation that can address all of those things is not a debunking of the curvature of the Earth. And what I have shown is that your examples are lacking. They are interesting, imaginative, but when scrutiny is applied, we see that they fail in many different ways. Now, I will look into this battle of the beams that you mentioned, and I will see if my explanation fits to it, and I will see what other explanations there are that explain it. But basically, everything we've seen here does not debunk curvature. It just, at best, provides an alternative explanation.
Thank you, Al.
Thanks. That was right on time.
Go ahead, Shane.
2 minutes. Yep. So I think we'll wrap that up nicely. I think we attacked bridges. I think that a 1 5/8 disparity at the top, I think we can safely say can be covered by other varied means of contracting or expanding, weight loading, having a tension be brought to it, all of it, the seasons changing, all of those things I think explain bridges. I don't think bridges are a good proof of curvature of the Earth. I think there's a reason why only flatearth.ws uses them. I think we went over the horizon a lot. We went over bottom-up obstruction. I think that was a good one. I think the radio horizon argument definitely could have went stronger for you. I think Battle of the Beams is a really excellent point for us. It's never been debunked. There is no refutation. There is no geometric way that is possible on a globe. We checked. We asked many people. If we go into the bottom-up obstruction being proved by top-down obstruction, I think that's a really good argument. I think if my argument is that I'm explaining, what you have previously attributed to physical Earth curve with an optical explanation, and then I'm furthering it by saying if it is an optical explanation, then we should be able to reverse it and have the same effect from the top down given the circumstances. And I think looking at a building in top down and approaching it from the bottom gives the same effect from the top. Therefore, it concludes that the bottom of obstruction would also be an optical effect. You said I didn't disprove curvature, but it's actually never been proven. By providing an alternative explanation for the phenomenon that has previously been mysteriously attributed to physical Earth curve, what we've done is dissuade people of the need for it in the first place, meaning that if it can be explained for optics, why would people ever say that the ships are going over the horizon when all we'd ever want to say is, look, they're going into the horizon, past here into the resolution limit, right? If that was the case, we would never need Earth curvature. The fact that it's never been substantiated is why I can list optical explanations as a surrogate for the phenomenon and why I think that is sufficient. But also, I want to thank you for having a really, I think, polite, courteous debate. You're really nice to debate you. If you want to go again, I'll definitely do a different topic with you.
Excellent. Let me make sure we have no super chats. I don't think I saw any come across. Nope, I don't see any over here. Let me check Rockfin, but I thought it was very polite as well. So thank you for doing that. I don't have anything else. So Eyal, tell people where they can find you if they're interested in more of your knowledge and work.
Look for me on Twitter. Can you put the username for me on Twitter?
Sure. You mean in the description?
Yeah.
What's your
At
username?
Lev Eyal 111.
Yeah.
So at LEVEYAL 111.
Okay. Got it.
And also, if I can share with you or send you the links that I used in my example or the whole document.
Absolutely. Yeah, we'll put it all in the description.
Yeah. Send me a message in Twitter and I'll send you the text.
Sounds good. Okay, and where can we find you, Shane?
Always ADL.place. Someone tried to help me by promoting my YouTube, but I just want to realize that's not going to be around forever. I will eventually be deleted from YouTube once again. ADL.place is where I will live and where all my channels will be able to be found from there. Tomorrow, definitely check Alan out. He'll be back on your show debating Mortarwand, and then we'll have I'll be running the watch party Ether Cosmology and Reverse It.
Beautiful.
So check us out then.
6 p.m. Pacific, so join us for that. Should be fun. And I believe that is it. All right, guys, we'll see you tomorrow. Thank you for joining us. It's been fun. We will talk to you soon. I remind you, do your own research. When you do, you'll never again believe all the bullshit you've been taught. Till next time, this has been Debatism. Peace.
Thanks, everyone.
Yeah. Yeah. It was nice just hanging out. Now go and hit the bell. Share it with the homies so that they could grow as well. They missing out. Jaren leaves no doubt. If you know what we bout, it's never for the cloud, don't fuck around. Hey, not for the clout, that's too cap, we calling them out. Balls get flat when you cover the route. Jeranism all in your mouth. Truth gets lost like all on the couch, but it's time to get up and make them get out. Uncover the route. Jeranism, we are the crown. Telecasting worldwide, check the globe is falsified. Space is spinning, DFI, all just scientism lies. Telecasting worldwide, check the globe is falsified. Space is spinning, DFI. All just scientism lies.
Who this be? What he about? You stay spinning, he said out. About flat earth, it's flat out. He's still standing when you passed out. Globers pound, screaming, shout. He can turn you inside out. Yeah, surface deep, he's felt throughout. And he stay grounded, you spaced out.
We gotta run nowhere when we come fact check your facts and match your data. Concept is too abstract, what matters? Try to tune in, but the note get flatter. Tell me I'm flattered. Flatter than pancake batter, now we landed. Jeranism, I'm your captain. Speaking, telecasting worldwide. Check the globe is falsified. Space is spinning, DFI, all just scientism lies. Telecasting worldwide. Check the globe is falsified. Space is spinning, DFI, all just scientism lies. You know equations to the things you make the symbols for, but ain't really explaining what the symbols for. They try to teach you things against the things we taught before. No point in arguing now, they don't wanna talk no more. Okay, got a bite of the truth and now it's certain. That's what life look like when your mind is certain. Okay, got a bite of the truth and now it's certain. That's what life look like when your mind is certain. Thanks to the east side, thanks to the west side, thanks to the north side, way down to the south side. Thanks to the east side, thanks to the west side, big ups to the north side, way down to the south side. Telecasting worldwide, check the globe is falsified. Space is spinning, DFI, all just scientism lies. Telecasting worldwide, check the globe is falsified. Space is spinning, DFI, all just scientism lies. Telecasting worldwide, check the globe is falsified. Space is spinning, DFI, all just scientism lies. Telecasting worldwide, check the globe is falsified. Space is spinning, DFI, all just scientism lies.